Hello everybody. Today we're going to go through the answers for the gaseous state. There are 15 MCQ altogether. Alright, so let's start from the first question, the ACGC Prelim 2018. Okay, they say what will happen to the volume of a bubble of air submerged in water under a lake at 10 degrees Celsius and 2 atm. So what happens if it rises to the surface where the temperature is 20 degrees Celsius and the pressure is 1 atm. Alright, so what they're asking for is the volume of the bubble. Alright, so we can have to assume that the number of moles of the gas in the bubble, right, doesn't change. So using PV equals to nRT, right? So the number of moles of the bubble doesn't change, the R doesn't change, so only pressure. Oh, they also mention so pressure, volume and temperature will change, which means PV over T, they are variables, and nR is their constant. So I say PV over T is actually a constant, isn't it? So we're going to apply this formula, P1 V1 over T1 equals to P2 V2 over T2. So the pressure for the first part is 2 atm. Alright, the volume, okay, I put VI, initial volume, alright, when it's submerged in water. Okay, the temperature is under the lake, right, it's actually 10 plus 273 because I need to change it to Kelvin. So once it rises to the surface, the pressure is 1 atm. Alright, and the final volume which of the bubble I'm not sure yet. That's what we're supposed to find. And then 20 plus 273. Alright, so you just have to press your calculator and do some manipulation. So you're gonna find out that VF will turn out to be 2.07 VI. Alright, so you play around with you just do the moving of the equation. Yeah, so this is what you're gonna see. So you can see that the volume will increase by a factor of 2.07. Right, so this is the final and this is the initial. Right, so that's why the answer is B. Okay, let's look at the next question. Okay, let's look at the next question. Right, which of the following graphs are correct for about a fixed amount of an ideal gas? So when they say fixed amount, don't forget it means the number of moles is a constant. N is a constant. Right. Okay, so let's run through. If I use PV equals to nRT, okay, I'm just doing the first one, P versus V, right? So P is equals to nRT 1 over V. As you can see, pressure and volume are inversely proportional, so this graph is definitely correct. Okay, so for the second one, PV equals to nRT. If you plot a graph of PV versus T, just like this, PV versus T, alright, nR is actually your gradient, which means 2 is definitely correct. So this is a slope, is a positive gradient, okay, sloping upwards. Okay, let's look at the next one. PV equals to nRT. So we know that N and R are constant, so PV over T is a constant, right? Right, so once you bring the T across, it's equals to nR, which is actually a constant. So if PV is a constant, I would expect to see a vertical line because this value is a constant, right? So which means 3 is also correct. Answer is all of the above, right? Okay, let's look at question 3. Okay, there's ammonia and there's hydrogen, not hydrogen, HCl, all right, in separate bottom flasks. All right, so they were, then after that what happens is they open the gas tap joint, all right, and the gases are allowed to mix. They say what's the pressure of the resultant gas mixture. Okay, so this question is a bit tricky. Theoretically, you can see that ammonia and HCl, they are actually not inert. In fact, one is an acid, one is a base. So which means ammonia, we have HCl, alright, they are gases, alright, and they'll form ammonium chloride. Okay, they're going to form ammonium chloride, which is actually a solid. Okay, the only thing about this question is you have to take note, it's actually a reversible reaction. Okay, this actually is a reversible reaction. Maybe you've learned this in secondary school. Actually, this reaction is reversible. Okay, so I'm just gonna say this. So typically, if the volume, if there's no change in volume, so we're gonna take it as a P because PV equals nRT, right? So I'm going to take it as if volume doesn't change, right? Pressure and moles are proportional if volume and temperature doesn't change. I think this question, the temperature didn't change, but of course the volume did change, because once you open the gas tab joint, all right, actually the volume which both gases can move around has actually increased. Okay, but I'm just going to tick it as the volume didn't change first. All right, so I think pressure is proportional to number of moles. So you can see that there's 3 atm over here and 4 atm over here. So if they do react, and they react in a ratio of 1 to 1, right? If they do react, I'm going to say ammonia is the limiting one, minus 3 atm. So HCl also will react minus 3 atm. All right. So in the end, there's no more ammonia, but there's 1 atm of HCl. All right. So this is a solid, so I don't really bother about it, yeah, because we're talking about the pressure. So we're only looking at the gases. Okay. So if there's no change in volume, the pressure will in the end be 1 atm. But the truth is this, this HCl, this remaining amount of HCl, in fact, it is, at first the volume was 250, right? At first it was in a volume of 250. After the gas tab is open, it can move around in a volume of 500. Okay, you can see that it can move around in a volume of 500. Yeah, so if it can move around in a volume that's double, all right, I believe the pressure will actually half. All right, I believe the pressure is half. So if it's theoretically, it should be 0.5 atm. All right, theoretically it should be half of 1 atm, 0.5. But take note, okay, this reaction is what? Reversible. Okay, this reaction is reversible, which means maybe not all the HCl, I guess not 3 atm of HCl reacted, probably less of it reacted. Okay, probably less of it reacted. So which means the answer has to be somewhere between 0.5 and 1 atm. It won't be exactly 0.5. This will be marked wrong. Okay, why won't it be exactly 0.5? Because this reaction is reversible. So when we calculated 0.5, assuming it was a straight arrow, but because this reaction is reversible, there'll be actually a slightly more HCl left behind. It won't be 1 atm, right? There'll be slightly more, so it has to be between 0.5 to 1 atm. All right, so this is a bit of a tricky question, okay, but answer it should be C. All right, okay, let's look at the next question here. Okay, which graph correctly describes the behavior of fixed masses? So fixed masses, again, N is a constant, the number of moles is a constant. Yeah, so if I did PV equals to nRT, all right, so you can see that constant temperature. So if temperature is constant and N is a constant and R is a constant, PV is a constant. It's okay. So PV is a constant, which means I can eliminate A and B. Because PV is a constant, the graph should be a vertical line. All right, this means PV is a constant. Okay, let's look at the next one. PV equals to nRT. I'm going to plot V versus T. All right, so V is equals to nR over PT. Okay, and since the question is only asking for which graph is correct, right? So I guess you can see from here, they say I has a higher MR than J, right? So number of moles is actually equals to mass over MR, okay? R over P times T. So this whole part is actually your gradient, okay? Notice this is your gradient because you plotted V versus T, all right? So V versus T, this is your gradient. So R is a constant, P is a constant because constant P, right? So mass is also constant, all right? Fixed mass. So the only difference is the MR. So the thing is, since I has a higher MR, so if you have a higher MR, in fact, the gradient implied the gradient will be actually smaller. All right. So the gradient will be smaller, which means it's actually more gentle. Okay, more gentle. So I would have a smaller gradient. So which means the answer will be C. Okay, let's do a question 5. Right. If you have attended my lesson, you have known this. All right. So if you see a straight line, it's actually what I call the ideal plot, right? Ideal plot. So there's this thing called negative deviation and positive deviation. So when the graph goes down is negative deviation, when it goes up is positive deviation. So this part here actually represents negative deviation from the ideal line. So negative deviation is actually due to the gas has significant intermolecular force of attraction. Alright, so the part that goes up over here, when it starts to go up, right, or in fact it starts from here, once it goes up, so when it starts to go up, we say it is actually positive deviation. So positive deviation is when the gas has significant volume, because when you under very high pressure, when this y-axis actually this x-axis actually is pressure, so very high pressure, when you compress it until very high pressure, all right, actually the molecules of the gases actually would occupy a significant volume compared to the volume of this container. All right, so that's the idea. Okay, so this question is asking at which point of graph is the intermolecular force of attraction the dominant factor. So the significant the intermolecular force of attraction is the dominant factor, is where you have the negative deviation. Okay, negative deviation. So which means this answer must be, okay, this answer must be W and X. All right, so this is gonna be B. Right, answer is gonna be B. All right. Okay, so let's move on to question 6. Okay, look at question 6. A container with a volume of 421 bar and 293 Kelvin, all right, is joined to another container here. Right, these are the conditions, but over here in the middle is a vacuum and 13 meter cube. Okay, see, so once these containers are all combined, all right, and temperature allowed to reach 298 Kelvin, they say what is the final pressure in bar. All right, so I'm just going to assume there's a gas X over here and say there's a gas Y over here, just for calculation's sake. All right, so since when the gases, when the taps are open and the gases can move, right, what doesn't change is the number of moles of gas X and number of moles of gas Y. Right, so I'm just going to use PV equals to nRT. If the number of moles of gas X doesn't change, R doesn't change, all right, which means PV over T is actually a constant. You see that? All right, so we're going to do for gas X, all right, and after that we do for also gas Y. So let's look at P1 V1 over T1 equals to P2 V2 over T2, okay, for just gas X. So the initial pressure is 1 bar, volume is 420, temperature is 293 Kelvin. Okay, the final pressure of gas X, right, is Px, right, and the final volume you actually have to add all of them up. Okay, so the total volume after adding them up is 420 plus 13 plus 75.5. So if you all add all of them up, okay, the final volume will be, let me see, I calculated just now, 508.5 meter cube. All right, so this X can now move throughout this whole setup, and the volume is 508.5 meter cube. So this is 508.5 meter cube. All right, and the temperature now is 298. All right, so if you try to calculate, do the math, you try to calculate this, you get 0.840, okay, bar. Again, okay, because this was actually in bar, so this one will also be in bar. All right, okay, let's try the next one. If I try to do for Y, I do exactly the same thing. So gas Y in here, so P1 V1 over T1, so P is 2, V is 75.5 over 273 equals to pressure of Y. Now the Y also can actually move throughout the whole entire setup, so it's 508.5 divided by the temperature 298. So you calculate PY, I got 0.324 bar. All right, so which means now the total pressure, all right, total is PX plus PY, so which is gonna be 0.84 plus 0.324, right? Press your calculator, you get about 1.16 bar. All right, so that's why the answer is C. Okay, let's move on to the next question. Okay, question 7. All right, question 7. Okay, I think this one is still quite okay. So this gas F actually deviate more for ideal behavior, it deviate more, and gas E deviate less. So if gas F deviate more, it means it will have significant intermolecular force of attraction compared to gas E. Alright, so we should look at the option. Gas E could be helium while F could be CO2. So helium and CO2, they're actually non-polar, okay, but so they both ID. But carbon dioxide, because it's a bigger molecule, it has more electrons, okay, it has more electrons, imply it will have stronger ID, all right, compared to helium. So which means it will deviate more from ideal gas behavior. So this why A is the answer. Okay, this one I think should be fine. Okay, let's look at question 8. Okay, so there are two gases here. No, there's actually one gas only. F contains helium at this pressure. G has been evacuated, means it's a vacuum, and has 3 times the volume of F. All right. So when the valve is open and the helium can move throughout the whole apparatus, all right, they say what's the final pressure of the system. So the same thing, the number of moles of helium doesn't change. So we're going to apply the same concept. P1, all right, times V1 over T1, okay, because these are the conditions that changed. P2 over T2. Okay, the initial pressure of helium is 10 to the power 5. The volume, I let it be V first, okay, and the initial temperature is 20 plus 273. The final pressure, that's what you're supposed to find. The final pressure of helium, that's what we're supposed to find. Okay, now helium can, if this is V and this is 3V, the total volume is actually 4V. So the helium can actually move around in a volume of 4V. Can you see that? So you divide by the temperature, which is 100 plus 273. Okay, you realize that the V can just cancel out, all right, can cancel out, and then you just have to calculate. So the pressure for helium, okay, we work it out nicely, all right, you should get a value of 3.18, okay, times 10 to the power 4 Pascal. This is to 3 SF. Okay, so this one you have to work it out, and you can see the answer. All right, so the answer for 8 is A. Okay, let's move on to the next question. Okay, which factor is the most significant in explaining the non-ideal behavior of gases present in the reaction chamber in Haber process? So to explain the non-ideal behavior. So to have non-ideal behavior, all right, generally to be non-ideal, it must have negligible volume and as well as have significant. To be non-ideal, it must have significant volume, all right, and significant intermolecular force of attraction. So this will only happen at high pressure and low temperature. Okay, so which means you're going to look out for conditions that has either high temperature, high pressure, or low temperature. So if you look at it carefully, right, for this question 9, okay, the answer has to be D, because the high pressure of 150 cause the molecules to be quite close, so would have significant intermolecular force attraction, and the volume is not negligible anymore. Right, so that will explain the non-ideal behavior of the gases, right, in the Haber process. Okay, let's move on. Okay, question 10. Okay, the volatile liquid is injected into gas range at 97 degrees. Initial reading was 5, and then the final reading was 81, and the pressure was kept constant at 97, and atmospheric pressure is 1 atm. Okay, so when the syringe stops moving, the outside pressure is 1 atm, but the inside pressure must also be 1 atm. So what it means is this. So imagine if a syringe stops moving, okay, imagine the syringe stops moving, outside pressure is 1 atm, inside pressure must also be 1 atm, right? Okay, so we're going to just apply the formula PV equals to nRT. So what is the pressure of the gas, right? The gas is actually 1 atm, so I'm going to use 101,325. Okay, the volume is actually the difference. Okay, the volume is actually the difference between 81 and 5, right? So it's 76, right? 76. So 76 I convert to meter cube is times 10 to the power minus 6, cm cube to meter cube. Okay, the mass of the gas, which is 0.253 divided by the mr. Okay, divide by mr, and then after that you can, let me just get over here. Okay, you multiply by 8.314 or just 8.31, I think it's fine. Okay, and of course the temperature. Okay, the temperature was kept constant 97, so put 97 plus 273. Alright, so calculate your mr. Okay, work it out nicely. Calculate your mr, work it out. You should get 101. Okay, so that's answer. It's D. Okay, let's move on. Question 11. What's the volume of vapor formed when 10 cm cube of liquid ethanol? So you need to know what's ethanol. Ethanol has a formula of CH3, CH2OH. This ethanol. So the mr of ethanol is actually 46. Okay, you work it out. It's 46. So let's try to use the formula PV equals to nRT. So they want you to find out what's the volume. So this is the unknown. All right. So 5 bar means 5 times 10 to the power 5. 1 bar is 10 to the power 5 Pascal. Volume is unknown. The number of moles of ethanol. So you have density times the volume, okay, which is 10 cm cube. That will give you mass only, yeah. So mass divided by the mr will give you the moles. Then multiply by, of course, 8.31 multiplied by the temperature. Okay, 300 plus 273. Okay, work it out. Okay, work it out. Your volume will be in meter cube, but once I convert to cm cube, it should be 1633 cm cube. Okay, but if you do the math, at first it was a meter cube, then you multiply by, if I'm not mistaken, it should be like 1.633 times 10 to the power minus 3 meter cube. So after that, if you want to change to cm cube, is 1.633 times 10 to the power minus 3 times 10 to the power 6. Alright, cm cube. Okay, so 1, 2, 3, yeah. So that's why you get 1633 cm cube. Alright. Okay, so that's D. Okay, let's look at the next one, question 12. Which of following graph represents the variation of PV with temperature for fixed amount of an ideal gas? So fixed amount, which means number of moles is a constant. PV equals to nRT. Alright, so N is a constant, R is a constant. You are plotting PV versus T. Alright, and T normally is in Kelvin, right? It should be in Kelvin. So this part here, NR, is actually your gradient. Okay, so that is your gradient. So if you will get B if T is in Kelvin. But T is not in Kelvin, it's actually in degrees Celsius. So for temperature that's in degrees Celsius, you must plus 273. Alright, then you can convert to Kelvin. So if that's the case, since this is in degrees Celsius, the graph has to be translated to the left. So the answer is A. Alright, so you actually looks like this, and here where it cuts is minus 273. Okay, so that's why answer is A. Okay, let's look at the next one, 13. Which diagram correctly represents or describes the behavior of a fixed mass of an ideal gas? So using PV equals to nRT, you must be able to look at it very quickly. So volume and temperature, they're proportional, which means this is actually correct. Okay, pressure and volume, they are inversely proportional. In fact, it should look like this. Okay, but of course cannot touch the axis. Alright, so maybe draw nicely. So this graph should look like this. Alright, PV versus P, right? But PV equals to nRT, and T is a constant, R is a constant, N is a constant, PV is a constant, should be a straight line. Same goes for this one, PV should be a straight line. Okay, so the answer has to be A really. Okay, let's move on to the next question. Al2Cl6 decomposes into AlCl3, right, in this 250 cm cube closed vessel. Yeah, they maintain temperature at 500 and the pressure at equilibrium, okay, is actually this pressure. So the average MR of the equilibrium is found to be so much, okay. So if you try to draw AlCl3, you know that it looks like that. Okay, we did this in chem bonding. So AlCl3 is like this. So the bond angle is trigonal planar is 120. But if you try to draw Al2Cl6, you should know it looks like this. It forms a dimer. Okay, it forms a dimer. And Cl, because Al only has 6 electrons, it needs 2 more. It gets the lone pair from Cl, gets the lone pair from Cl. So the shape about aluminum is actually tetrahedral, okay, because it has actually 4 bond pairs and no lone pairs. So the angle actually becomes 109.5 actually, right? 109.5. So this answer is wrong already, okay. Alright, okay, so for question for part 2, if you did calculate, you can actually do some calculation. Alright, you can do some calculation. They say the mass of the gaseous mixture inside was 1.5 grams. Okay, so how do you prove that? But if you look at the option, right, since 1 is wrong, actually the answer is obvious. It's going to be C really. Alright, but just let me show you very quickly. If you have to work it out, right, the pressure, we're just going to use PV equals nRT. So the pressure is 1.16 times 10 to the power 5. Volume is a closed container, so this times 10 to the power minus 6. Cm cube changed to meter cube. This is the mass we should don't know. Then you divide by the average MR, which is 214.9, then 8.31, and then multiply by the temperature, which is 500. Okay, you work it out really. If you work it out, you'll find out that mass will also be 1.50 grams. Okay, which means this statement is correct. Okay, so this one here, because it's larger, it has more significant IDID. All right, more significant IDID. It will deviate more from ideal gas behavior, so you should see a greater deviation. Okay, compared to this one, right? Compared to AlCl3, less deviation. All right, so this last statement is also correct. Okay, so answer is 2 and 3. Right, 2 and 3. Okay, let's look at the next question. Okay, during the operation of a refrigerator, the coolant is constantly being liquefied and vaporized once the pressure is released. Under these conditions, the gas does not behave as an ideal gas. So which statement best describes why gas liquefies under pressure? So when they liquefy, it doesn't behave as an ideal gas. So the thing is, if you compress it very hard, right, the molecules actually comes closer and closer. It would actually have significant intermolecular force attraction, okay, because the molecules are very close. So when the increasing pressure will push the molecules closer, so that the short range intermolecular force attraction becomes more effective, which means it becomes stronger. Okay, so it becomes stronger, the gases can come closer and they can become a liquid more easily. Okay, they can become a liquid more easily. All right, okay, so that's why the answer has to be D. Alright, so that's it. Thank you for watching the Twig Learning Center chemistry tutorial. I hope you learned something new. Don't forget to click the subscribe button so you'll be updated when new videos are posted.